So we are learning about the memory systems, okay? And then actually we did not cover the storage systems actually. So the storage system is a very slow memory, right? So we can store our data in the storage system like hard disk drives or the SSD, the solid state drives, okay? And then so what are the features of these storage devices? These storage devices are slow and also the density is high. So as I mentioned, and then it's cheap. Also, another characteristics of these storage devices is it's non-volatile memory. So that means the data is not erased even though the power is off. Okay, so that means the non-volatile memory. Right? But the DRAM or SRAM are volatile memory, so it means the data are erased if the power is off, right? So I believe we already know, right? So so let me briefly explain, okay, about these storage systems. So these are non-volatile memory, and then also it's slow. So, and then also for those SSD, SSD includes the flash memory, right? Right? And then, this flash memory looks like this, okay? As you can see, these are flash memory chip, right? And then, so it looks like a DRAM chip, right? It's because it's a kind of the product of the semiconductor, right? So, so compared to the hard disk drive, the flash memory is much faster, right? And then I will explain about the hard disk drive later, but so this is the solid state. So it means it's the kind of uh, semiconductor devices, right? It works with the electric signals, right? So which means, so compared to the mechanical systems, electric systems are much faster, right? So think about the some mechanical devices like some machines are actually very slow, okay, compared to the our electric devices, right? So the flash memory is the solid state memory. So that's it means it's very fast, okay? It's much faster than hard disk drives, okay? So hard disk drive, as I mentioned, hard disk drive is the mechanical devices. What does that mean? A hard disk drive includes mechanical motor, right? And then this motor rotates the uh, plate, okay? So these are called the plate. So as you can see, this is the plate, okay? And then actually our data is stored on the surface of plate, okay? So actually the motor rotate the plates, and then also you can find the arm here. So it's called the arm. And then also the last part of the arm is called a head. And then head read writes the data from the surface of the plate, right? So it means actually because the motor rotates the plate, it means the hard disk drive is extremely slow, right? So you can find some example here, okay? So this is the example of hard disk read time, okay? And then so actually, so this is the seek time and then rotation latency, but you can find that the seek time and rotation latency, it is determined by the rotation speed and then also the speed of arm, okay, hard disk arm, right? And then as you can see, the time unit is millisecond, right? And then so we are learning about the computer systems working with the nanosecond time unit, right? So 1 gigahertz. So you know, but the clock period of 1 gigahertz clock signal is 1 nanosecond, right? So actually, the electric devices is work with the nanosecond time unit, but the hard disk drive is a mechanical devices, so the time unit is the millisecond. So milli is the 1/10 to the power of -3, nano is the 10 to the power of 9, right? So compared to this time unit, so you can find that, oh, it's very slow, okay? It's about a million times. So the million times slower than our computer system. So that's why the hard disk drive is very slow. Okay, but so recently our devices use the SSD. So I mentioned that the SSD is much faster than the hard disk drives. So as you can see, it's around but it's around 1,000 times faster than the disk. So it is because the latency. The latency of this flash memory is around the microsecond unit. Okay, so around one it's around the 1 microsecond or 0.1 microsecond. So and then also the DRAM, DRAM is around the tens nanosecond latency. Okay, have the tens nanosecond of latency. Okay, so compared to the DRAM, the flash memory is 100 times or 2,000 times slower, right? But it's also the 100 times or 5,000 times faster than the hard disk drive, right? So you can just understand that hard disk drive is extremely slow, right? But it's cheaper than the solid state drive. Also, the density is higher. So which means we can also use the hard disk drives to store our data, right? But what kind of data? So think about the memory hierarchy, right? In the memory hierarchy, the high level memory is fast, and then we store frequently used data in the high level memory, right? Storage is slow, right? Also, the hard disk is much slower than the SSD. Then, if our data is rarely used, then we can store this kind of data to the hard disk drives, right? So, based on the characteristics of the memory systems, then we can also uh, identify the what data will be stored in the which level of memory systems, right? Okay, so you can understand this. Okay, so it's a hard disk drive, but in this class, in this course, we will not learn about the hard disk drive. So it is because usually the storage systems are managed by operating systems, not hardware. So hardware just supports the protocol, like the NVMe or SATA protocols, but these storage devices are actually managed by operating system. So it is because these devices are slow. Okay, so we can use software for managing slow devices, so slow components, computer system. So that's why the operating system manages the storage devices. But the memory, the DRAM is much faster than the storage systems. So DRAMs are mainly managed by hardware, right? So fast components are managed by hardware, and then slow components are managed by software, right? because software is slow, okay, compared to the hardware units. Okay, so we learn about the storage systems in this course, right? Because the storage systems are managed by operating systems. So think about the file system. So you can think that the file system is a kind of hardware, but actually, like the NTFS or so the Linux ext4 file system. So actually, the file systems are software. Okay, so we can actually change the the software code to make the new file systems. Okay, okay, so let's learn about the cache. It is because so in the memory hierarchy. Okay, let's go to the previous pages. Okay, so in the memory hierarchy, the cache. So register file is managed by hardware, obviously. So right. So when the instruction is executed, then registers are updated by hardware. And then cache. Cache is also managed by hardware. So we will learn about the cache in this time. The main memory. Main memory is also managed by hardware and software, actually. So we will learn how the software, like operating system, actually, operating system manages this main memory. So, right, in the later, okay. Okay, let's learn about the cache. So then what's the definition of a cache? Okay. And then, so, as I mentioned, the pronunciation of cache is actually equivalent to cache. Okay. It's right. So I also mentioned that actually the computer architect frequently use a dollar sign for representing cache, right? Like the L1 cache. Okay. It is because the pronunciation is the same, but actually, the the letters are different, right? But the pronunciation is the same. Anyway, what is the definition of a cache? So if you search for the meaning of a cache, then you can find so there's many definitions, right? So in the real world, cache represent the hiding place. So like uh 비상금 숨겨놓는 곳. So it's a hiding place for money, right? So usually, this is it's a normal definition of cash. But as a computer science students, so you need actually understand the definition of cash in the computer system. So what's the definition? Definition is, as you can see, it's cache represents a temporary storage space or memory. Okay, it's a temporary space. Okay, the data is temporarily stored in cache. For what? This is the purpose of a cache that allows fast access to data. Okay, so when you learned about the instructions in chapter 2, we learned that instructions update the states in the computer system. And then these states are registers and memory, the main memory, right? So our instructions just update the registers and memory. You cannot find caches, right? So it is because the caches are temporary storage space. Okay, the data is temporarily stored in the cache. But for what? So this is the purpose of the cache. The cache supports the faster accesses compared to the main memory, right? That's why we a computer system includes a cache. Okay. Okay. So now I will explain. I will exhibit the analogy of cache in the real life. Okay. So actually, so in the real life, okay, so we frequently use the concept of caching. Okay, so actually, so we are learning about the hardware cache in a computer system or computer processors, but in a software, we also frequently use the terminology cache. Okay, so actually, so for example, the web browser cache, okay, the contents are just cached in our computer system because the servers are far from our computer system, and then servers are slow. So we frequently use the terminology cache or cache in the hardware and software. Anyway, so in the real life, in the real world, actually, we frequently uh, utilize the concept of caching. Okay, so what can you observe in this figure? So you can find that in a bookshelf, there are many books. Okay, there are many books, and then you can think that these books are kind of data. Okay, but in this figure, you can find also the pile of books. Also, you can find the several books on the desk. So actually, there are many books. We can access these many books on the bookshelf, but in order to access, so access means that we need to pick the book from the bookshelf, and then we can read the the pick the book, right? But this bookshelf is far from our desk, right? So in order to access the books in a bookshelf, then it will take long time. But in the real life, we just focus on a couple of books. So for example, if you are preparing for the exams, then you can just focus on one or two books or one or two textbooks for preparing for the exam, right? So in this case, we just put our books on the desk, and then we frequently access these books. We do not put these books on the bookshelf because it is cumbersome, right? So if we find the computer architecture book on the bookshelf, and then it will take a very long time to pick this book from the bookshelf. And then after you completing your some study, then if you return the book on the bookshelf, then it will also take long time. But we already know that we will read this computer architecture book in the short time, right? So then we just put this book on the desk, right? But there are only couple of books. What does that mean? The size is small. We cannot store all books on the desk. We can just pick the frequently used book on the desk, but we can just put only a small number of books on the desk, right? But what's the benefit? We will only focus on the couple of books in real life. And then if we can find these books on the desk, then we can quickly access. We can quickly find the target books on the desk. It's a concept of a cache, right? It is possible because we only focus on a couple of books, not all books, okay? So there are many books here. So which means that we can have some chance to access many data, right? Large amount of data. But actually in the real life, we only utilize a small portion. Okay, so small part of data. Then we can just store this small amount of data, but it's a frequently used data on the close to us. Okay, by doing this, we can reduce the access time, right? We can save time in the real life. Okay. Also, we can just put the couple of the large number of books on the desk instead of bookshelf, right? Then it is because we can also easily access these uh, piles of books. Okay, so you can understand the caching like this. Frequently used data or frequently used something is close to us in order to reduce the access time. But the space is small, right? We can just store a small number of books or only the couple of books close to us, right? But it's okay because we will only read a couple of books, right? We will not read the entire books on the bookshelf within a short time window, right? So in the real life, we also the utilize the concept of cache or caching. Okay. Then, so we learned that our application also exhibit a very strong data locality. So which means the spatial locality and temporal locality, which means only a small portion of data. So actually the memory is very large, so we can store entire data in our memory, right? But only a small portion of data will be used within a short time window, okay? Then we can store this data in the faster memory. But this fast memory is very small. We cannot store all data, right? That's the concept of cache, right? So the cache is here. So as you can see, this is the register file, and then actually the instructions access register file. So we learned that the register file is very small and then very fast, right? And then also this is the main memory, and then this is the register file. And then using the load instructions, like load word or store, also the store instruction, we just transfer data from memory, what we just transfer data to memory. So these memory instructions, load instructions and store instructions move data between register file and main memory, right? And then as you can see, you can find the cache. And then cache is located between register file and main memory. So, which means, we, but this cache is very fast, but the size is small. So when these instructions, the load instructions and store instructions transfer data, we can store the data in the cache, right? Then what's the benefit? If this data is frequently requested by load instructions, so actually the load instruction is critical for the performance of a computer system. If the data is frequently accessed by load instruction, and then if this data is found in a cache, then we can reduce the access time, which means we can increase the performance of load instruction, right? So you can understand the cache like this. So, and then as I mentioned, so actually in chapter 4, we learned about the process architecture. Okay, so and then we learned that there are two types of memory, instruction memory and data memory. But actually, these are level 1 instruction cache. Oops. Level 1 instruction cache, and then this is the level 1 data cache. Okay. So what does that mean? This is the temporary memory, right? So actually in the instruction cache, the size is small, it's smaller than the main memory, so, which means it's very fast, right? So, and then we learned that actually from the instruction memory, but actually this is the instruction cache. So from the instruction cache, we can fetch data within one cycle. So which means it's very fast. Okay. It is because in the DRAM is the main memory. The latency of DRAM is tens nanosecond, right? So it's slow. But cache, the level on cache, we assume actually it's not true in the modern computer processors, but it's fast. So we assume we can read data from this level of instruction cache within one cycle. That's why the instruction fetch takes one cycle, right? How about the data memory? The data, actually, this is the data cache. So load instructions and store instructions access this level 1 data cache. And then we assume that also in chapter 4, we assume that the load instruction takes only one cycle, right? But the duration is very, very slow, right? So actually this is the cache. So this is very fast. So if the request data is found in this level 1 data cache, then we assume it will take only one cycle. Okay, it's fast. So now you need to understand that this is the level 1 instruction cache, and then this is the level 1 data cache, right? Okay, then when we design a cache, then we need to consider these questions. So first, what is the first question? The first question is that what data is held in cache? So which data needs to be stored in the cache? So, I mentioned the cache is temporary memory space, so storage space, right? We cannot store all data in the cache. It is because the cache size is small, right? Then what does that mean? We need to select which data will be stored in the cache. So what data is held in the cache? Answer? No. Answer? Frequently accessed data. Okay. So in the cache, we need to find the frequently accessed data, right? If the rarely accessed data is found in the cache, so that cache is not helpful for increase the performance. So we need to store the frequently accessed data in the cache. Then how is data found? So cache is a temporary space, which means a data can be found or data cannot be found in the cache. Also, we need to identify the request data is in the cache or not. How can we identify how, how is data found? How can we identify the request data is in the cache or not? So question, how can we identify data in the memory. So how can I identify a student is here or not? So, so we can use the the real student. I mean, okay. So we can use the self-attendance check system. But anyway, so we cannot distinguish if the real student check this system or not. Okay, right? So actually, so we can identify students with the student ID, the student number actually, right? How is the data identified? Using address. Okay, so the memory address, right? So if we so in a code, in a C code, if we just declare the variable that I mentioned, that the memory space is assigned to this variable. So computers cannot understand the alphabet letters, right? So how can a computer identify variables? Using address. A computer can identify data using address of data in the memory. Then how is the data is found? We can identify data using the address of data. Then what does that mean? So this is the small space, and then which means the data needs to be stored in this small space. But we need to identify the request data is really in the cache or not, right? Then what is required? Because we cannot store all data in the cache. So in order to identify data in the cache, which means address. Address information also needs to be stored in the cache along with data. Right. So for example, we request data A, but we know the data A is in the memory, right? But we don't know the request data A is in the cache or not because it's a small. Then in order to identify this data, then we also need to store address of data in the cache along with the real data. Okay. Then if the address is matched in the cache, then we can know, the request data is in the cache, right? So you need to understand this. Then what data is replaced? So what does it mean? The cache space is small. The cache cannot store all data. So it means if the cache is full, then a part of data needs to be replaced, right? So think about this analogy. So if you complete the study of the computer architecture, then you need to replace the book on the desk, right? So replace is required. So what data is replaced? So I mentioned that in the analogy, if you complete the study of computer architecture, what does that mean? We already know we will not use computer architecture book, right, anymore. Then this book can be replaced. So ideally, if the data is not used any long, is not used anymore, then we can replace it. So this is the ideal case actually. But so if we know the data will not be used, so what does that mean? This is the future event. right? So a computer hardware cannot know the future event exactly, obviously, right? It's just kind of the the area of God, right? The future event, right? So we don't know. So answer is the data is if the data will not be used anymore, then this data needs to be replaced. But actually, in reality, we don't know the future. So if we expect if the data is if the data is rarely used, okay? If we just uh, it's just estimation. So if we just estimate that, oh, a certain data will not, so it will be rarely used, then this data is replaced, which means the data is evicted from the cache. So when we design a cache, we need to think about these questions, right? So what data? The cache needs to store the frequently accessed data. How data is found, we also need to store address along with data. What data is replaced? If the data is just estimation, just the prediction, right? If the data will be rarely used, then we can evict this data from the cache. So evict means it's kicked out. Okay, it's replaced. Okay, okay. So the cache. So so this is that so it's a level of memory hierarchy closest to the CPU. So as you can see, so in this memory hierarchy, you can find the cache. Okay, and then the level of cache is between register file and main memory. But also in this figure, so you can find that there are multiple levels of cache: level 1, level 2, level 3. So actually, in the inside of this cache level, so there are multi-level caches, level 1, and then level 2, and level 3. So usually, the commodity CPUs include level 3 caches, okay, up to level 3 caches, okay. So, and then the cache just to store the data, the frequently accessed data. Okay. Then when the data is allocated, so we just call the data is allocate. So this is called the data allocation, right? So it means so data was not in the cache, right? But the new data is stored in the cache. And then this event is called a cache allocation. So the data is allocated in the cache. So when the data is allocated, oh, okay. So think about the load instruction. So load instruction requests data. So it's a load instruction x1 and then so offset x2 like this. And then this is the address in the memory. So we already know that the load instruction transfer data from, so this is the register file, and then this is the memory, and then load instruction read data from memory, and then the load instruction store data in the register file, right? That's what we learned. So, but now we learned that the cache is here, right? Cache is between the register file and memory. So when the data is allocated, so when the load instruction is executed by CPU, then firstly, we check the cache, right? Because the cache is the temporary space. So think about this. So we want to find the book, right? In this analogy, and then firstly we need to check the books on the desk, and then if the book is not found, then we will check the pile of books on the desk, right? Like so, when the load instruction is executed, then firstly the CPU check the cache. And then if the data is not found, then we need to transfer data from the memory, right? So which which means the request data was not in the cache, right? So data will be transferred to the register file. And then when the data is transferred to the register file, this data is newly allocated in the cache. Okay? So do you understand? When the memory instructions are executed, then the CPU firstly checks cache. And then if the data are not found, so which means that the data was not in the cache, then the data needs to be transferred from the low level cache or memory. So in the memory, then this newly requested data. So because the cache does not have this data, the newly requested data is allocated in the cache. So, and obviously this data is also transferred onto the register file. What does it mean? Cache is checked, but if there is no data, the data is not found in the cache, then it means the data need to be transferred from the memory. Then when the data is transferred from the memory, this data is also allocated in the cache. Okay, this how the cache is cache the data, how the cache allocates the data. Okay, then we need we need to also decide where the data is stored. So what does that mean? So cache is also the memory. It's a small memory, right? So what is the memory? So memory has multiple entries, right? So memory has multiple entries, and then we store data in the one of these entries. Then we need to store the location, which means we need to decide on where the new data is allocated. Okay, so I mentioned the cache includes the many entries because it's memory, right? It's also kind of a memory, but it's a small memory, right? So it means each entry has the address actually, right? But this address is called the index. Okay, so the sometimes you may be confused because in the memory devices the address is given, then we can get some data. But sometimes we also used a terminology, the different terminology such as index to represent the address. Actually, so address of the memory, right? But cache, so because the cache is different from the main memory, so we use the terminology index. And then index represent the actually the entry number. Okay, so we can just number the number 0, 1, 2 to the number n for each entry. So index represent this entry number, right? Then how can we decide? So how can we decide the entry number entry number of the cache entry which will store the new data? Okay, so we need to make a rule. Okay, so for example, uh, so this is the classroom, right? So and then I can say that in the left side, in the left side of a classroom, only if the student ID number is the odd number, then the student need to sit on the left side of the classroom. And if your student ID is the even number, then you need to sit on the right side of the classroom. So what does that mean? So based on the student ID, I just distinguish the location of student in the classroom, right? So what do them? And then in the cache also we need to decide the location of data, okay? And so which means a newly allocated data can be stored in the specific location, specific index of the cache. Okay, so for example, so as I mentioned, as I said, using the even number and odd number of your student ID, I just distinguish the location of students, right? Cache is the same because cache cannot store all data, then which means we need to decide the location of data. So in order to decide the location of allocated data, then we can use the address of data. So you need to distinguish index and address of data. So this index represents the entry number in a cache. Address, this is the address in main memory, right? So using using the address of data, we can access the data, right? So and then I also mentioned that using the address, we can identify data, right? So as also we can use this address for determining the the location of a cache entry, okay? The target cache entry. And how? So I took the example of student ID, right? If the student ID is old and it's the left side, even on the right side. So what does that mean? Using the address, then we can also determine the target location in a cache. So for example, if the address is 0000, then we can, but if the cache entry, there are 4 cache entries. Oh, what does them? If there are only 4 cache entries, then we can use the lower 2 bits for identifying target index in the cache. Do you understand? So which means if the last 2 bits, the LSB 2 bit is 00, then data is stored in the index of this index of cache, index number 0. And then if the last 2 bits is 0, 1, then this data is stored in the this index, this entry, the index number 0, 1. Okay, and then 1, 0. So this 1 is stored in the 1, 0. Okay, so this is how the target entry number, target index is determined. But so think about this. So if the cache, so actually the cache includes many entries. So this entry is also called a block. Block or cache line. Okay. So an entry in a cache is also called a cache block or a cache line. So think about this. If the cache block size is 1 byte, then is it efficient? It's not efficient. Why? So think about the size of integer. So size of integer is usually 4 byte. And then, so, computer, also in chapter 2, we learned about the memory instructions, but usually we use the load word, right? And then load word just request 4 byte of data, right? So if the cache block size is 1 byte, it's too small, which means if the word data, the 4 byte of data is requested, then the 4 byte of data will occupy the 4 blocks. But usually, well, we hand our computer system handle larger data, right? The word data or double word data. Also, you can think about the spatial locality, right? So which means we just use the near data, right? So which means the cache size, the cache block size need to be larger. Okay. So usually the cache block size is larger than 1 byte. And then in a CPU, usually the cache block size is 64 byte. Okay. So and actually this number is determined by the RAM, right? But anyway, so you can just understand that the cache block size is larger than 1 byte, right? So you can find that it's in the direct mapped path, direct mapped cache. So you can find the block address is the modulo is applied, and then we just get the modulo result from the block address. Then this block address represent the address of cache block size. So you may it so because so you may be confused at this time because uh, when we mention simply address, then it represents the address of data. And then we learn that address number 1 represents the 1 byte, okay, in the computer system. But in this slide, I mentioned block address. So which means this address is determined by the block size of a cache. So which means, if the cache block size is 64 byte, which means block address 1 occupies 64 bytes of data. Do you understand? So, so there are multiple blocks in the cache, and then each block size is 64 byte, right? And then when you mention the block address 0, okay, then this block address 0 occupies or covers memory address 0000002. Oh, no, it's a 6. 111111. Okay, so this amount of data is allocated in the cache, right? So when I mention the block address 1, so block address, then it represents the address for this cache. Okay, and then it's determined by it's determined by the size of cache block. So this is the example. So in this example, you can find the memory, and then you can find also cache indexes here. So in this example, the cache has 8 entries, and then also the memory has multiple entries, right? So the memory is larger than the cache, right? But you can find the cache index here, and then you can find some address here. But this address is the block address, not real memory address. Okay, not real memory address. Okay, so when you mentioned, so in this example, the cache has the 8 entries. So the cache index range is from 0 to 111, right? Because the cache includes 8 entries. Then cache index 001 can only store the block address 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1. What can you observe? If the last 3 bits of the block address, is a block address, okay, is a 001, then these blocks are only stored in the cache index 001. Okay, and then this is another example. If the last 3 bit is a 010, then these blocks are mapped to the cache index 101. Okay, so this cache is called a direct mapped cache. So direct mapped cache means that actually the cache index. So one cache index includes only one cache block, and then actually the index number of the cache. So this cache entry is mapped to the multiple memory blocks. Okay, and then the lower bits decides the target cache index. So this is the direct mapped cache. Okay. Okay. So also, so I mentioned when the data is stored in the cache, we need to also store the address, right? But actually, in the direct mapped cache, we don't need to store all bits of this block address. Why? So, you know, in the using based on the direct mapped cache mapping rule, the address mapping rule, the index number is identical to the lower 3 bits of block address. So which means if we just find a target data in this index, then we already know that oh, this the address of this data is 101. Actually, the lower 3-bit address of this data is 101, right? To think about this, so I just said make the odd number student in the left side and the right number, even number student to the right side. And then if I pick the one of the student from the right side, then I already know that the student ID of this the ID of this student is even number, right? It's the same. In this cache index, in this cache entry, we already know that the lower 3-bit of this address is 101, right? So in this case, we don't need to store this data. Instead, we need to store the upper bits, right? In order to identify the data in this index, then we need to store these upper bits, right? Then we can know the address. So actually, we do not store entire bits of the memory address. We just store the required data. So usually the upper bits, okay? Because the lower bits are determined by cache index number. So these upper bits are called the tag, okay? So instead of storing all address bit, we in the cache only the tag is stored. Okay, so the part of address, and then using this part of address, we can identify address of data. Then we can check the request data is in the cache or not. Okay, so this is the tag. So actually, the tag is stored along with the data. Also, the cache has the control bits. It's called the flag. Okay, and then this flag just represent the status of the data. So in this example, there is the valid bit. So if the valid bit is 1, it means that this cache index includes the valid data. But if this valid bit is 0, then this cache does not include the valid data. Okay, so cache also includes the cache flag. So it's the control bit. So this is the example. Okay, example of the cache. So you can find the cache index here. So you know this is the index number, right? And then this B represents the valid bit. So cache flag. So it's a tag and data. Okay, and then this is the configuration of the cache. Cache includes the 8 block, right? And then the size of block is the 1 word. So what does that mean? It's 4 byte. Okay. The size of a single block is 4 byte. And then it's a direct mapped cache. And then initially, the all cache entries are invalid. So which means there is no data. There are no data in the cache. No valid data. So cache is empty, right? Initially empty. And then let us assume that the load word is executed by CPU, and then this is the word address. Okay, so 22, and then actually when we convert this to the binary address, and it means the 10110. Okay, so I mentioned this is the word address. So it's a 4 byte, actually, 4 byte. And then which means one cache block size is the one word, one 4 byte. Then what's the real address, real memory address? The real memory address is 101100000, right? Okay. But in this example, I just used the word address. So which means address number one covers one word data. It's a 4 byte of data. Okay. So you need to understand this. So actual memory address is 1011000. Okay. But I just used the word address. Okay. So you need to distinguish this. So load word is executed, and then this word is requested. Okay. So it is requested, but and then I mentioned that the CPU firstly check cache, but the data is not found because the cache is empty, right? So then this is the block address, right? It's because the cache block size is the one word, right? And then this cache has 8 entries, which means we will use for the direct map to cache, we will use the lower 3 bit of the block address as the index of the cache. Do you understand? So in this case, the target index is the 110. Okay. So it's missed in the cache because the data is not found. And so new data needs to be allocated. Allocated where? Index number 110. And then the remaining address. So we need to store the remaining address. So it's the upper address 10. So this is the cache tag. Do you understand? We do not need to store entire address bits. We just store the upper bits. Okay. And then the data. So this address is the word address, right? And then the cache valid bit becomes 1. So in this case, we use Y, but it means 1. And then the next turn, another load word is executed. So the word address is 26. And then, so it's a binary form. And then we just use the lower 3 bits as the cache index. Oh, cache index 101. But this entry is empty, right? So result is miss. Okay, it's missed in the cache. So the data is requested to the memory, and then data is transferred, and then new data is allocated in the cache. So what is the tag? Upper bits. So tag is 11, and then this data is stored in the cache. Okay. And then the CPU execute the another load word and then another load word, but this load word requests the word address 222 and then 26, right? And then binary. So in this example, so it's a binary 10110, and then we use the lower 3 bit as the cache index. So if this cache index number is 110, we check the target entry 110. And then target entry has the valid data. In this case, we compare the tag. So what is the tag? What is the tag of this load word? Tag is 10. And then what is the tag of stored data? The tag is 10. So what does that mean? Tag is matched, which means the cache has the requested data. So in this case, the data is provided from the cache. Then the result is cache hit. 26 is the same, right? Because index is here, and then valid, and the tag is matched. And then, so 16, 30, 16. So also you can find you can figure out the result of the cache access. And then 18. So what is different? In the 18, the index number is 1010. So it's the same. But when we access the cache using the cache index number 010, then it is already occupied, and then but tag is 11. This tag is different from the tag of the request data. So what does that mean? The target cache entry, the target cache block includes the valid data, but different data, right? Because the tag is not matched. So in this case, what's the result? The result is miss. Because the target, this data is not request data because the tag is not matched. Okay. So cache works like this. So the cache is organized like this. So this is the address, and then you can find this is the byte offset. It is because, as I mentioned, the cache tag size, the cache block size is larger than 1 byte. Okay, so the lower bits are used for the byte offset, and then we use the lower bits as the index of the cache. So it determines the target cache entry, right? The index, and then this cache has the 1024 index cache blocks. Okay, so the range of index is the 0 to 1023, which means the index bit is the 10 bits. Okay, and then we store the upper bit. This upper bit as the tag of the cache. Okay, so this is how the cache works. Okay, so you need to understand this. Okay, this is very important part. Okay, oh. Okay, thank you for your attention, and then see you in the next class. 감사합니다.